Hi, I'm Mikey, and today I want to share with you some great insights I've learned from some really experienced, talented engineers over the years, and hopefully this is going to help you get to the next level as an engineer. I would like to also apologise for the fact that I'm wearing a hat indoors. There's still a lockdown here in the UK and I haven't had a chance to cut my hair, so it's all over the place right now, so I thought I would just tame it with this annoying hat. Apologies for that. The first insight that I've got for you today is that your code is probably too complicated. One big thing that I found when working with really experienced engineers versus more junior ones is that the experienced ones really try to opt for the simplest solution they possibly can in order to solve the problem. Now, when you first start out coding, what tends to happen is that you don't really know that many techniques. So you might know how to write an if statement, you might know how to define a function, so your code will be relatively simple in that respect. At this point, your code would probably be quite concrete in that it's not that easy to change, and so if you had new requirements coming in, you'd have a little bit of an issue adapting your code to meet them. However, there would be a level of simplicity due to the lack of abstraction. As you get a little bit more experience, you learn a few more language features, say in Python or JavaScript, if those are your main languages, and you learn about, how to write a decorator or how to write a context manager or how to do MapReduce in JavaScript. Something that can end up happening is that you end up trying to use every single piece of knowledge that you have in all areas of the code base. So you think, I've got this problem to solve. How can I do it with a meta class? Or how could I do it with a MapReduce? Or how could I do it with a decorator? But in reality, you probably could have just hard-coded it, or you probably could have just used a simple loop. So this is like the other end of the spectrum. You've got your concrete code here, not very easy to change, a little bit of duplication, and then you've got your really abstract code here. You've got to follow loads of layers to try to work out what's going on. Now, as you become more experienced, you'll find that you've kind of go all the way from this side to this side and then kind of slowly back into the somewhere in the middle again. There's a great book about this called 99 Bottles of OOP by Sandy Metz. And this was introduced to me by a fantastic architect in one of my previous workplaces. And it really kind of opened my eyes as to how I personally like to overcomplicate things. So the task is very simple. I'm going to link it in the description below, in fact, so that you can have a go at it. But it's basically a coding exercise where you have to print the lyrics to a song. And the song is mostly the same, apart from the first verse and the last two verses. And when I was first tasked with this exercise, I wrote the most hideous, incomprehensible thing because, that's just kind of what I thought was the right way of doing it. But then my tech lead showed me that actually I was just overcomplicating it, and I could have just allowed it to be a little bit more duplicatey, if that's a word, a little bit more concrete, and that would have actually accomplished a much cleaner solution until, at least, we learned of any more incoming requirements. So my initial solution to this problem really, really sucked. It was basically incomprehensible, and I think it just about worked, but not really. And if I looked at it the day after, I wouldn't really understand how any of the code worked. My tech lead's solution, however, was 3 or 4 if statements, some hard-coded strings, and that was it. And it hadn't even occurred to me that I could have accomplished it so easily. So the insight here is really to take a step back and have a look at what you're doing occasionally and think, do I actually need to make it as complicated as it currently is? As Sandy Metz puts it, I'm going to read, as programmers grow, they get better at solving challenging problems and become comfortable with complexity. This higher level of comfort sometimes leads to the belief that complexity is inevitable, as if it's the natural, inescapable state of all finished code. However, there's something beyond complexity, a higher level of simplicity. Infinitely experienced programmers do not write infinitely complex code. They write code that's blindingly simple. So when writing code, we need to be able to strike a balance between something that's too concrete and something that's too abstract. Something that is difficult to change but easy to read, and something that is less easy to read but more open to change. Now, if you get the abstractions wrong, then you might not be open to change anyway. That's something else that she talks about in the book. So I really recommend checking out this exercise and giving it a go. The second insight is picking the right tool for the task. Less experienced engineers are more likely to pick tools that they like as opposed to tools that are more suitable for the job. I once heard a junior developer say that they didn't think that Python is a real programming language. I don't know, maybe because it's slow compared to C++, or maybe it's because it's too easy to learn compared to C++. But the context matters. If you're building a web application, you're much more likely to get mileage out of writing it in Python or JavaScript as opposed to writing it in C++, because those languages are so much more expressive. Yes, Python is slow when it comes to just executing code, but when you're writing a web application, the main bottleneck is going to be in the I/O. You're going to have way more bottlenecks in waiting for the database to retrieve that information than you are doing any number crunching. In this case, writing the web server in C++ is going to cost a ton more engineering time. It's going to take ages to get any features out for your company. And all in all, it's going to end up costing a lot more money. On top of this, junior engineers also love using technologies because of the hype around them. This also extends to architectural designs and patterns. Really experienced engineers aren't going to use a pattern or a design just for the sake of it. You may or may not have heard the term cargo cult programming. The term refers to the usage of concepts and designs in programming just because you think they should be used, as opposed to understanding the core benefits that these techniques provide you. Cargo cult programming is a very typical thing for less experienced engineers to do, but I think everyone falls into the trap of doing it sometimes, and I definitely still see myself doing it occasionally. Sometimes it's good to just take a step back and ask yourself, why am I doing this? Is it because it's how I've seen everyone else do it? Do I understand the core benefits for the way that I'm approaching this problem? One recent example in architectural design is microservices. Microservices have been this kind of almost buzzword in the last 10 years or so in software engineering. I've seen some startups opt for microservices from the very, very beginning when they're building a product. However, really experienced engineers and architects don't go for this approach because they understand that microservices shouldn't be used for the sake of using microservices. They should be used when you have specific challenges that microservices will help you solve. For example, a good reason would be to scale a particular part of the product. However, if you're simply using microservices because you think it's going to make your code cleaner, then you're probably missing the point. If you can't write a clean monolith, you probably don't have a chance in writing clean microservices either. The bottom line is just because it's a popular trend or something that you like doesn't mean that it is the best tool for the job. In my experience, senior engineers are always thinking about that when they're presented with a new problem. The next insight is that it's really important to break down large tasks. I've seen this with less experienced engineers where they'll be given a task and about a day or two later they'll come back with this massive pull request and there'll be loads of changes, it'll be impossible to review, and it's going to have a bunch of conflicts with what's going on with the rest of the code. So the tip here is to make a habit to ask yourself, is this task that I'm working on too big? If it is there a way for me to break it down into smaller, digestible chunks that are easier for everyone to review and easier to spot mistakes in? For example, if you are trying to replace an old piece of functionality with a new one, you might, write a new module or a new class, and it's completely fine for you to check that in before you plumb it in with the rest of the code. You don't have to do it all in one massive change. If you need to do a little bit of refactoring, it's fine to do it upfront as a kind of initial change before you get cracking on the real work. That's assuming that the refactoring isn't massive in itself. Smaller changes are really beneficial in that they make things much easier to review, and these atomic changes are much easier to hone in on when bugs are introduced. Lastly, readability is one of the key characteristics of good code. As part of the first insight, I already talked a little bit about readability, but I'll go into a little bit more detail here. The truth is this: writing code that works is not that difficult. You can take a grad from university or from a development bootcamp, you can tell them to write you an app, and they'll write an app and it will probably work. The difficulty isn't getting code that works. The difficulty is writing code that is sustainable in that it allows for growth. As a product grows, businesses want to be assured that they can easily add new features and that whilst they're doing that, they are going to minimize the chances of causing any breakages. Without good code readability, development slows down. Not only do developers need to spend ages trying to understand how the code works before they can add a new feature, but the same also applies for fixing defects. How can a team move quickly if they can't easily understand how their code works? Next time you're writing some code, be aware of the trade-offs. If you want to squeeze a little bit of performance out of the code, how much readability is that going to cost you? And is it worth that? If you're specifically trying to tune the performance, maybe, but if you're just writing a new feature, you may have heard the phrase that premature optimization is the root of all evil, and this certainly applies here. The same goes for reducing duplication and reducing the amount of lines in your code. If you were to do that, how much readability is that going to cost you? This is something you've got to be thinking about every day when you're writing code. So that's all I have for you today. 4 insights from some really talented, experienced engineers that I've worked with in the past. Hopefully they're going to help you get to the next level as well. Thank you for watching. I really appreciate this. If you like this kind of content, press that subscribe button with the bell icon, and I'll let you know when the next video comes out.